Okay, now let's have a look at the example for energy balance for one component process. We have two streams of H2O mixed to form the feed to a boiler. Stream 1, the mass flow rate is 120 kg per minute at 30 degrees C. Stream 2, 175 kg per minute at 65 degrees C. And we have boiler at 70 bar pressure. The exiting steam emerges from the boiler through a 6 cm ID pipe. The flow rate of the saturated steam at the output boiler is 295 kg per minute. Calculate the required heat input to the boiler in kilojoule per minute if the emerging steam is saturated at boiler P. Neglect EK of the liquid inlet stream. Okay, so if we draw a flow chart, we have two inlets where these are the inlets, and then we have outlets here. Then the most important thing is we need to level the mass flow rate for both inlet and also for outlet, and also we need to put the condition, the final condition of the pressure at the outlet, which is 17 bar saturated. And then we also have 6 cm ID pipe as the where we can find the area of the pipe later on. Now what we need to do is we use energy balance for an open system. Since there are no moving parts, we can assume Ws equals 0. No potential energy because no elevation in the system. So delta P equals 0. So what left is delta EK. Why delta EK is not 0? Okay, we go back to the questions. Okay, if you go back to the question, we know that it only asks us to neglect kinetic energy for the liquid inlet streams, but not for the outlet stream. That means for kinetic energy, we need to find outlet kinetic energy minus with inlet kinetic energy, which is 0. Okay. So if we go to the solution, how to solve this. Okay, this is the flow diagram that we have sketched previously. Okay, but before that, we can use steam table for system of water and saturated. Because from the question we know that the outlet is the saturated steam, so the inlet is the saturated liquid. So we need to refer to table B.5 or table B.6 to solve this question. If we go to table B.5 to find the value of inlet, okay, look, we have 30 degrees C and also 65 here. So let's say we want to put 65 degrees C. So we need to do interpolation because we don't have 65 degrees C here. We have 64 and 66. So we do interpolation and then we can get the value of enthalpy, okay, for water. Okay, for water. If we do interpolation here, this is not the formula that you need to memorize. Like I mentioned before, you can plot or you can sketch a graph, then you find the slope, and then you can get the value of the point that you want. So this is the slope formula actually, but you don't have to memorize this formula. Just use the slope of the straight line. So after we do extrapolation, the value for enthalpy at 65 degrees C is 271.9, and the same goes to 30 degrees C. If you cannot get the value from the table directly, you need to do interpolation. If you can get the value directly, you can straight away take the value from the steam table. Okay, so the value is 125.7. And the same goes to the outlet where we have saturated steam. So at 17 bar, so the value will be 2793 kilojoule per kg. Okay, how to get this 2793 kilojoule per kg? We go to table V.6, where we go to 17 bar, we go to steam. Okay, the enthalpy, okay, sorry, okay, the enthalpy for steam is 2790.4. Take the enthalpy for water because the outlet is at steam condition. And also at this condition, we need to know the value of specific volume for steam, 0.1166, which is stated in this table, because later on we are going to use it to find the kinetic energy, because in the question we have the formula, we have the internal diameter of the pipe for outlet. So what we can do to find the kinetic energy, we have this formula, and then since we can neglect inlet, so this is the formula for outlet only, where if we divide volumetric flow rate with the area, we can get velocity, such as being discussed in the previous class. Okay, so to get volumetric flow rate, what we need to have is the mass flow rate and also the volume. So if you look at the mass flow rate here, 295, where we can get from the outlet, and then if we times with the specific volume, and then we can cancel out kg with kg here, so we get meter cube per minute, and we convert the unit to second, we can get meter cube per second. So in other words, we get the value of volumetric flow rate here, and also we can find the value of area because the of pipe is 6, so this is the radius, pi r squared, and then we convert the unit, and then later on we convert again the unit until we get kilojoule per minute. So this will be the final answer for this question, 0.6.02 times 10 to the power of 3. Sorry, not the final answer, but the kinetic energy for this system. Okay, then we go to the next step, where just plug in the value that we have, where previously, after omitting potential energy and also the work done by the shaft, because both gave 0 value. So we have Q equals delta H plus kinetic energy, and then delta H is 7.61 times 10 to the power of 5 plus with 6.02 times 10 to the power of 3 kilojoule per minute for both. And then finally we will have change in heat at 7.67 times 10 to the power of 5 kilojoule per minute. So additional information, if we need to deal with this kind of problem, it is safe to neglect EK and EP contributions as a first approximation only for process involve phase changes, chemical reactions, or large T changes. Now we have the final problem for energy balance. This is for two-component process, where we have a liquid stream containing 68% ethane and 41% N-butane is to be heated from 150K to 200K at a pressure of 5 bar. Calculate the required input per kg of the mixture, neglecting EP and EK, using tabulated enthalpy data for C2H6 and C4H10, and assuming that mixture component enthalpies are those of the pure species at the same time. Given the enthalpy for ethane and N-butane when the pressure is 5 bar are 314.3 and 30 kJ per kg at 150K, and 434.5 and 130.2 kJ per kg at 200K respectively. So we just draw a flow chart. Okay, this is the inlet and this is the outlet. And why do we call this as the two-component system? Because we have two components, which is ethane and N-butane. Previously we have water only, but the water have a different state, which is liquid and also vapor, but still one component. Here we have two components, ethane and N-butane. That's why we have the we have the mass fraction here, okay, to let us know the composition of each component in the system. Okay, so how to solve this question? It's very easy. Since we don't have kinetic energy, no potential energy, no work done by the shaft, we only have H equals Q. So Q equals delta H. Since we need to find Q, so we can look at the change in enthalpy. Summation of outlet enthalpy minus with the summation of inlet enthalpy. Referring to the value given in the textbooks, we can get the value of enthalpy output for C2H6, okay, which is at this part as 434.5 because the condition is at 200 Kelvin 5 bar. Okay, the same goes here at 200 Kelvin and 5 bar. We have 130.2 kilojoule per kg, where it is given in the question actually. Okay, it is given here at 150 Kelvin. These are the values of enthalpy for both components, and at 200 Kelvin, these are the enthalpies for both components. So we just plug in the value in the formula. So this is the summation sign, means we need to sum up the enthalpies for both component at outlet and for both component at inlet. And then if you look here, the mass balance is still the same because there is one inlet and one outlet, no change in mass. So we have the same mass here, okay, for outlet, for inlet, for outlet, and for inlet. Just the only difference is the enthalpy values because there are differences in the temperature for outlet and inlet. So after you solve this part, you will get this value 112 kg per second, and then the question asks you to find the specific value. So that's why you need to divide with the total mass flow rate here, where 1 kg per second, so you get 112 kilojoule per kg, because second and second you can cancel out the unit. Okay, that's all for the energy balance that we want to learn. Okay, so please watch the video. Please ask me the question if you don't understand anything related to this part. Hope to see you in the class soon. Hope we can do the tutorial together so that you can have more understanding regarding this topic. Okay, that's all for today. Assalamualaikum warahmatullahi wabarakatuh.